What are SSVEPs for optimizing BCI performance? Imagine controlling a computer or a wheelchair just by looking at flickering lights. Sounds like science fiction, right? Well, it is actually a real technology called brain-computer interface, or BCI. Today, we're going to explore how a special brain response called steady-state visual evoked potentials, or SSVEPs, help make these systems work better. SSVEPs are signals your brain produces when you stare at a flickering light source. These lights flash at specific, steady frequencies, and your brain responds by generating electrical activity at the same rate. This activity happens mostly in the back part of your brain, called the occipital cortex. When a person focuses on a flickering light, their brain's electrical signals lock onto the flicker's frequency and phase. These signals can be picked up by sensors placed on the scalp, usually with a device called an electroencephalogram, or EEG. In BCI systems, SSVEPs are used to translate what someone is looking at into commands for external devices. For example, if you look at a flashing icon on a screen, the system detects the brain's response and interprets it as a command. This makes SSVEP-based BCIs very accurate and stable, which is important for reliable control. They don't need the user to move muscles, making them especially useful for people with motor impairments. To improve how well these systems work, researchers use several strategies. One way is to choose flickering frequencies that produce the strongest brain responses. Certain frequencies, usually between 5 and 25 Hz, work best. Using multiple flickering lights at different frequencies, or even dual-frequency stimuli, allows the system to recognize more commands. This means you can control more devices or perform more complex actions. Another key is designing the visual stimuli carefully. Instead of plain flashing lights, some systems use checkerboard patterns or even QR code designs. These patterns can boost the brain's response and make it easier for the system to detect signals. Plus, good design reduces visual fatigue, so users can stay engaged longer without discomfort. Signal processing techniques also play a big role. Methods like canonical correlation analysis or power spectral density analysis help filter out noise and improve the detection of SSVEP signals. This results in faster response times and more accurate command recognition. Combining SSVEP signals with other brain signals, like the P300 response, can make BCIs even more reliable. This hybrid approach takes advantage of multiple neural responses to boost overall system performance. Reducing visual fatigue is essential too. Flickering lights can cause discomfort if used for too long. So, optimizing flicker frequency and stimulus design ensures users stay comfortable and focused during extended use. In summary, SSVEPs are a powerful tool for making brain-computer interfaces more accurate and user-friendly. By carefully selecting flicker frequencies, designing effective visual stimuli, and applying advanced signal processing, we can improve how these systems interpret brain signals. This progress opens up new possibilities for assistive technologies, helping people communicate and control devices directly through their brain activity.